Alright, so this video is going to be about forces, and as I said in the last video about properties of motion, this video is designed to help you accurately evaluate how well you understand the concepts that you've learned about during GCSE physics. So the time to use this would be either at the end of your study of GCSE physics or at the start of study of A-level physics to make sure you have the right level of understanding that you'd be expected to. So let's get cracking. Okay, so first example, we've got an elephant and a feather, and they're both falling from a very high tree. Which encounters the greatest force of air resistance in falling to the ground? So would it be the elephant, the feather, or would they experience the same air resistance? So what you need to do is pause it so you can have a think, select your answer, and then we'll explain what you should have picked. All right, so let's take a look. Okay, so the answer here is the elephant because air resistance is affected by two things. It's affected by velocity and it's affected by surface area. So the surface area of an elephant is much larger, therefore it experiences a greater force of air resistance. Also, the elephant would end up traveling faster as well, so that would also give it a larger force of air resistance. However, what you see when you drop it is it appears that air resistance is affecting the feather more because you'll see the feather fall really slowly to the ground, whereas the elephant would just go whack straight into the ground. But it just looks like the force of air resistance is greater because its effect on the feather is considerably greater because the feather has such small mass. But the actual force itself would be much bigger on the elephant. It's just that its mass is so big, the effect of it is very small. Okay, so let's have a look at another one. So we've got a lot of flies that are trapped inside a jar, and you place the jar on a scale so we can measure the mass, or actually measure the force. So the scale will register the largest weight in these three different scenarios. So again, pause the video, have a think about it, and then select your answer, and then we will take a look at what you should have. Okay, so now you've got your answer. Let's have a look. So the correct answer here is the weight would be the same in both cases. So the easy one to understand is that when the flies are sitting on the jar floor, the scale would measure the weight force of the flies and the weight force of the jar, and it will give you a value. What's harder to wrap your head around is that if the flies are flying, what they would be doing is they would be pushing the air downwards. That's what allows things to fly. They push air downwards and they experience an equal and opposite force upwards. So if they are flying, that upward force must be equal to their weight force. So the downward force they are exerting on the air would be equal to the weight force of the flies, and then that air is pushing on the floor of the jar, so what it seems like is effectively you get exactly the same force. So that would be the answer we'd expect to get in both cases. Okay, so next one. So a strongman is pulling a spring apart. I don't really know why it has to be a strongman, but it could be anyone pulling a spring apart, never mind. And the spring is extending. Is there a resultant force on the spring? Again, so pause it, have a think, select your answer, and then we'll take a look. Okay, so now you've had a look at this one. Let's see what we should have had. So the answer to this question is no, there is not a resultant force. And that seems quite counterintuitive given that something is happening. So to understand this, you first need to have the knowledge that when you extend an object, you apply equal forces on opposite ends. That's how you get it to extend, but not the spring actually move left or right in this particular example. So in this scenario, there would be no resultant force because the two forces are equal and opposite. And in terms of explaining it another way, the center of mass of this object does not move. It just gets stretched further out. So when you stretch an object, if you actually stretch a spring, you'll feel it pulling back on you. And that's because when you stretch an object, a tension force is induced in the object that resists you stretching the object and tries to pull the spring back together. But again, those two forces are equal and opposite, therefore there's still no resultant force. Okay, so we have two scenarios. So we have on the left, we've got two blocks, each of them 10 pounds, and they are connected over a pulley. And then another scenario, we've got a 10-pound force, again with a string over a pulley, but this time it's just connected to something applying a 10-pound force. So the question is the acceleration greater in the first scenario, scenario A on the left, or the second scenario, scenario B on the right, or are they the same in both cases? Okay, so let's take a look at this. Now you've had a chance to pause and go through it and work out your answer. So the answer is B, we get a greater acceleration. So let's first discuss the things that are the same in both cases. So in both cases, the frictional force on the 10-pound object would be the same as with the frictional force at the pulley. So that's not going to have any effect on this. But what is going to affect it is the mass of the whole system. So on the left, the mass of the system is 20 pounds because we add them together. On the right, the mass of the system is 10 pounds. So we have half the mass, but we're using the same force to accelerate the system. So if you have the same force but half the mass, you're going to get double the acceleration with the system on the right, which is why the answer is B. Okay. So we've got two horses and they're both attached to a pair of jeans via rope. So the rope's tied to the jeans and it's tied to the horse, and the horses pull in opposite directions so that the jeans are stationary. And what that tells us is the two forces must be equal and opposite that allows it to be stationary. So it's kind of like the spring example earlier. So if one of the horses is replaced by tying the rope to a wall, what would that mean about the tension force? So again, I'll give you a second to have a think about your answer, maybe pause the video, select A, B or C, and then we'll see what you should have got if you understand this properly. Okay, so we can see the first example on the left. So we've got two horses supplying an equal and opposite force on the jeans. And then on the right, we've got one horse pulling on it, and because the rope is tied to a wall, we're going to have some kind of contact force from the wall that's stopping the rope moving. So if the jeans are stationary in both examples, that must mean the contact force is equal to the force from a horse. Therefore, we are looking at exactly the same scenario in both cases, so the tension force would have to be the same. So the force resisting stretching would have to be the same in both, and if the jeans aren't changing shape, which they're probably not, that means the tension force is big enough to resist extension. Okay, so let's have a look at a slightly different comparison example. So we've got a car and it collides with a wall at 50 miles an hour and becomes stationary as a result of the collision. We have another identical car, so same mass, hits the wall at 100 miles an hour and again becomes stationary from the collision. Then we have two more identical cars. I don't know where we're getting all these identical cars from. So again, each of them same mass. They're traveling at 50 miles an hour, but in opposite directions. So do the cars from the head-on collision look like the 50 mile per hour crash or the 100 mile per hour crash with the wall? So again, pause the video, have a think, select your answer and maybe think of some reasons why you think that's the answer, and then we'll take a look at what you should have got. Okay, so the correct answer is the cars look like the 50 mile per hour crash. So in this particular example, you can think about it a few ways, but in this case, I think it's helpful to think about it in terms of the acceleration. So in the 50 mile per hour head-on crash, each of the cars goes from 50 miles per hour to 0 as a result of the crash, which is the same change in velocity as when it went from 50 miles per hour to 0 when it hit the wall. So the acceleration would be the same in the head-on collision and the 50-mile-per-hour collision with the wall. And therefore, as the mass is the same, the force is the same on each of the cars. So that's the way you can think about it in terms of acceleration. Okay, so if you want to explore that last question in a bit more detail, I'd highly recommend you watch this video by Mythbusters on the force involved in car crashes, because this will actually show you a demonstration of this experiment and you'll actually see it for yourself, which is always good. So this is where I'm going to finish this video for today, looking at forces. I hope you found that useful to evaluate how well you understand the forces topic. If you have any questions at this point, please feel free to comment and ask me, and I'll try and get back to you as quick as I can. But thank you for taking the time to watch.